Why was the Ice Cube Neutrino Observatory built at the South Pole? Could you reignite a dying star by giving it more hydrogen? And what are the best places to go for your astronomy space bucket list? All this and more in this week's question show. It's time for the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops into your brain, just write it down. I will gather a bunch of them up and I will answer them here. Now, we do the show live every Monday at 5 p.m. Pacific time. So if you want to do a much longer show, it's around 2 hours long on a Monday. So set some time aside, but we do the show live. I answer questions, follow-up questions, and it's a lot of fun. So if you want that live experience, come join us. There should be a reminder somewhere on my channel for the next upcoming live event. All right, let's get into the questions. Brain bark. Why was the Ice Cube Neutrino Observatory built at the South Pole? One of my favorite observatories is the Ice Cube Neutrino Observatory, and this is a 1 cubic kilometer of ice near the South Pole with these boreholes that contain sensor packages all the way down deep into the ice. And so you get this, with all of the holes, with all of the sensor packages, you get this volume of ice. And then as neutrinos, either coming from the sun or from coming in other places around the universe, come through the ice, most of the time they pass through. I always say a neutrino can pass through a light year of lead without interacting. And so the vast majority of the neutrinos that pass through, nothing happens. But every now and then, one of them will interact with a piece of water, with a molecule of water, and then it will break up, spray into this shower of particles, and those particles interact with the detectors, and so they're able to recognize that the neutrino came through, created the shower of particles, and they can even sort of figure out where it came from because the shower of particles will move past various groups of sensors. And then they can use it like a telescope. And the amazing thing about neutrino detectors is it doesn't matter where you put them. Even if the sun's neutrinos have to pass through the Earth, they still can, no problem. And then they go through the neutrino detector and they release this cascade of particles, and so they're detected. So why put it in Antarctica? And the answer is because you need a place that has a lot of water, ice. And you need that place to be very clean, clear, unpolluted water. The kind of stuff that's been around for hundreds of thousands of years and hasn't been polluted, doesn't have like coal dust in it, things like that. And Antarctica is the perfect place. And there is a fairly large research station already near the South Pole. And so you can just add another experiment to the researchers that are there, and they can go out and they can stay at the station. They can do their work at the Ice Cube Observatory, and everything works great. Now, that said, there is another big neutrino observatory that is in the works right now from China, and they're planning on building their neutrino observatory at the bottom of the ocean. They've already scouted out a location, they've done some tests of putting them there, and their plan is to build the largest neutrino observatory on Earth in the ocean. It'll be larger than Ice Cube, and they're going to anchor their sensor packages to the bottom of the ocean and then have them sort of float up in this giant underwater grid. And the advantage of that is then you've got kilometers of water above where your detectors begin, and you're protected from cosmic rays and other stuff that's going to try to get through that water before it reaches where your detectors are. So there's still a lot of good places to put detectors on Earth. As long as we have oceans, we'll have places for neutrino detectors. And one plan in the works is to scale up the size of the Ice Cube to go from the 1 kilometer to a 10 cubic kilometer version. And so in this case, it probably won't have the same density of the sensor packages. It'll be less dense over a larger volume, but still you're going to have the ability to track neutrinos that are moving. And one thing that came out recently, which I think you should definitely take a look at, is astronomers working with the Ice Cube Neutrino Observatory. They took a photograph of the Milky Way, And it's not a real photograph, of course. It is a map of the neutrinos coming from all of the stars located in the Milky Way. And there was enough of them that they were able to create this image of the Milky Way, but in neutrinos, which is just amazing. So yeah, I love like neutrinos. I love the IceCube Observatory, and I can't wait for new versions, new ones to come online. I'm sure you've noticed the planet name that has appeared over my shoulder. You're going to see this again with every question that I do during this episode, and that's a way for you to vote, to tell us which you thought was the best question of the week. And normally I would tell you what the vote was for last week, but our system is broken right now, so Chad's going to have to put it up on the screen right now. Congratulations, you! Go ahead as you watch this video. You'll see the names of the planets, and then once the video is over, go ahead and put the name of the planet you thought was the best. All the names of the planets are down in the show notes as well, so you can do that as well. And then we will celebrate the winner next week. I'm Brezzy. Would it be possible for a dying star to reignite its main sequence fusion, or at least gain more life by absorbing a massive amount of hydrogen, whether it be from a gas cloud, a highly advanced species delivering it, or some form pulling in hydrogen for its fusion? So I think we have to sort of distinguish about what a dying star is. So when you've got a star like the sun, a main sequence star, it is fusing hydrogen into helium at its core. And it has a set amount of hydrogen at the core, and then that's surrounded by the radiative zone, and then that's surrounded by the convective zone. And when that star runs out of hydrogen in the core for fuel, then it starts to switch to other forms of fusion. So it switches to starting to fuse helium into heavier elements. And when that runs out, it starts to fuse carbon. And when it runs out of carbon, then a star like our sun will die. It'll go through these phases where it bloats up into a red giant, puffs out some of its outer layers, then comes back down, and then blows up again, and then comes back down, and eventually it has run out of all of the usable elements in its core, and then it just dies, and it becomes a white dwarf. And then it's already puffed off all of its outer layers. What you've got left is just the exposed core of a star. And that's like just side note, a white dwarf is the exposed core of a star that is now cooling down. It has gotten rid of everything else, and all that's left is that core, which is still actually a fairly big chunk of its mass. Like about a third of its mass is just in that core. So how do we save this? Well, it depends on when you want to save it. So let's talk about it like it's still a main sequence star, like the sun, and it's using up most of the fuel in its core, and you're like, we can save it! And so you feed it hydrogen. Well, when you feed a star like the sun more hydrogen, what you do is you shorten its life. The most massive stars, the ones with many times the mass of the sun, they go through their fuel very quickly and they die very quickly. Like a star like Betelgeuse is only a couple of million years old, and now it's almost ready to turn into a supernova, while the sun is 4.5 billion years old. And a small red dwarf star could live for 10 trillion years. And so you don't want to give it more fuel, because that will just make it explode sooner. What if it's in the white dwarf phase? Could you feed hydrogen to it to get it to reignite and turn back into a star? Well, no. And in fact, there's a certain kind of supernova that comes from a white dwarf feeding off a companion star. That's a type 1a supernova. So what you get is you get a white dwarf beside some main sequence star. It is absorbing hydrogen material off of that star, and when the white dwarf reaches 1.4 times the mass of the sun, they call it the Chandrasekhar limit, it explodes completely in a very violent explosion. The star is completely detonated, it's gone, and it puts off so much energy that we can see these things billions of light years away. And in fact, because it's that 1.4 times the mass of the sun, astronomers use this as a standard candle. They're like, oh, if we see a type 1a supernova go off halfway across the universe, when we see how bright it is, we know how far away it is. And so they're very useful. So no, unfortunately, the only way to make your star last longer is to starve it. You can't feed it. You have to take stuff away. If you take hydrogen away from the star, then you're going to be able to sort of shift it more towards the red dwarf size. If you take hydrogen off of the white dwarf, which sounds tricky, but we're in our imaginations, we can do anything, then you give it more ability to grow before it hits that Chandrasekhar limit and detonates as a supernova. So nope, you can't Save a star by feeding it material. You're only going to kill it sooner. Wayne Gnarly 1. I don't really appreciate the limitations you're putting on asteroid mining. Obviously, we won't send stuff back in OSIRIS-REx quantities. A couple of weeks ago, I got a question about whether it would be possible for us to mine asteroid Psyche and like, what is the future of asteroid mining? And I categorically said that we will never do asteroid mining. And people didn't seem to like that. We got a lot of comments down below that about people being quite angry that I was just deciding the future for humanity here in this moment. So I will respond to the arguments. And like, obviously, first, we don't know what the future holds, and we don't know what kind of technology is going to come our way, and we don't know what kind of infrastructure we're going to build over time, and who knows what's going to happen 200 years, 300 years, 1,000 years into the future when we have merged with our computer intelligences and we're turning Jupiter into computronium, and maybe it makes sense to mine more metals from the asteroids and feed them into the supercomputer quantum state machine at the heart of Jupiter. Like, maybe that's going to make sense. And there'll be a certain point where the computers will like beep boop and they'll make that decision and then they'll do that. But I think when people think about asteroid mining, they're like, that asteroid has got $1 quintillion worth of heavy metals on it, and iridium and all kinds of good stuff, and we could really use that stuff on Earth. It'd be worth a lot. And so wouldn't it be great if we could mine that stuff and bring it back to Earth? And the argument that I made and the argument that I still make is just that it's just too expensive. That if there were bars of gold, if there were bars of iridium sitting on the surface of Psyche, it would still be too expensive to build a rocket and to go and get them and bring them back to Earth. And in fact, there have been several asteroid mining companies that have been founded and they've gone out of business, and they've been founded and they've gone out of business. Like, the best way to go out of business is to start an asteroid mining company. Let's say that you want to send a return mission to an asteroid. You're looking at billions of dollars right now to send a return mission to an asteroid. And that is like, not like, let's send a regular return of lots of heavy elements back to Earth. Like, that's just like, let's pick up a rock. Let's pick up that brick of iridium and bring it home to Earth, which of course is not going to be iridium. It's going to be, you're going to require crunching up the regolith and turning and refining it and turning it into all these things. So there's all of this technology stack that's required. Right now, the cost to put about 1 kilogram onto the surface of the moon is in the tens of millions of dollars. 1 kilogram to put it on the surface of the moon. Not bring it back. Just like, if you wanted to take a brick, put it on the moon, you're looking in the tens of millions of dollars per kilogram. Like, you know, there'd be a bulk rate if you wanted to do more. And so you're always going to compete for price with a hole in the ground that's right beside you, right? That you, like, what is it going to cost to filter out iridium from seawater? What's it going to take to filter out gold from seawater, or to dig up any place that even has some amount of gold bearing rock in it? It's still going to be more expensive to do that. So what makes sense, and this, I think I said this before, and I'll continue to make this case, what makes sense is to use it locally. If it costs $10 million to deliver 1 kilogram to the moon, in other words, it's going to cost you $10 million to get 1 kilogram of water to the surface of the moon, why not, when you're at the moon, extract your water locally? It saves you the money to bring it up from Earth. Everything on Earth is at the bottom of just this enormous, awful gravity well that even if you like were right at the very ragged edge of the laws of physics, it would cost you an enormous amount of money to pull every single kilogram off of Earth and out into space. And so we won't need to bring stuff from space back to Earth because there's going to be so much need for stuff in space to bring stuff from space. And so, you know, you're not going to take that block of iridium and bring it back down to Earth. You can take that block of iridium and take it to the chip fab on the moon. Or you're going to build self-replicating robot probes out of the asteroid where you're mining it from, because it's going to be local. And eventually, we don't know what this is all going to average out to in the long term. But right now, today, it just doesn't make any sense. Eventually, we will work out this economy where it makes sense because of the gravity wells and the time frames to go from this asteroid, that asteroid, from the moon to Mars, from Mars to well, stay out of gravity wells entirely. From this nice place in space to that nice place in space. So, look, I understand that I am ruining sci-fi Christmas and thinking, and obviously you should never say never, but I feel pretty confident that we are decades, if not 100 years away from there being any viable reason to bring resources from space back to Earth. Rob Stewart, how is it determined that the Psyche asteroid is composed mainly of metals? So to figure out what something is made out of, you need to know its size and its mass. Then you can calculate the density. And normally this is done using a moon, because Newton's law of gravitation, if you have two objects that are orbiting around each other, the way the math works is you can figure out the mass of the two objects by the amount of time it takes for the objects to rotate around it and what the distance is and so on. But with Psyche, you actually don't have any satellites going around it. And so how do you figure out what is the mass of Psyche? And how astronomers figure this out is really clever, which is that there are other asteroids in the neighborhood around Psyche. Astronomers were able to measure how the mass of Psyche, the gravity of Psyche, shifted the orbits of these other asteroids that are located in the same part of the asteroid belt as Psyche. From there, they were able to calculate the mass of Psyche. They're also able to make visual observations of the size of Psyche, that you've got a powerful enough telescope. You can count how many pixels it's taking up. You can estimate what the size of this thing is. You can do even more accurate measurements using occultation. So you watch as an asteroid passes in front of a star, and that'll tell you exactly where the asteroid begins and exactly where the asteroid ends. And you can really put nice tight constraints on both the mass and the size. And once you have the mass and the size, then you calculate the density. And when you calculate the density of Psyche, you get something that's just about 4 grams per cubic centimeter. And like for comparison, that's actually a little less than the density of Earth, and Earth is made of metal and rock, but Earth also is enormous and has a lot of gravity that is pulling and compressing all of that rock and metal down into something that is more dense. But to have a density of almost 4 grams per cubic centimeter is significant for an asteroid compared to other asteroids. They're going to have a lot less. So astronomers were able to calculate the density. From that, they're able to estimate that it's some amount of metal and some amount of rock and then some amount of other volatiles. But it's more than water. Water is 1. So it's more than water. Rich universe. Are there different types of black holes? No, there's just different masses of black holes. So there are the supermassive black holes, the ones with millions or billions of times the mass of the sun at the hearts of galaxies. There are stellar mass black holes, like ones like Cygnus X1, black holes that are, say, maybe 10 to 20 times the mass of the sun. And the LIGO Observatory has detected the gravitational waves from black holes of 15 to 100 times the mass of the sun colliding with each other. Now, there are missing kinds of black holes that astronomers assume are out there. One is what is known as an intermediate mass black hole. So that's a black hole that's going to be more than 100 times the mass of the sun, probably more like about 1,000 times the mass of the sun. And when you think about, we have the supermassive black holes, the ones with millions of times the mass of the sun, they had to be built up with building blocks of black holes with lesser mass. So you would expect to see a ratio of black holes out there, some which are the mass of the sun, others which are 1,000 times the mass of the sun, ones that are 10,000 times the mass of the sun, leading up to the ones that are millions. But we don't see that. There's the millions, and then there's the stellar, and there's nothing in between. There have been some indirect observations. So for example, astronomers have looked at globular star clusters and noticed the movements of the stars in that cluster and assumed that you would have to have a couple of intermediate mass black holes lurking around inside that cluster to be able to get the kind of movements that you see. And then the other proposed idea is that there would be primordial black holes. And these are the black holes that were formed early on in the universe when there were regions of over and under density in the earliest states of the universe. And you would have black holes just forming naturally of all different masses, ones that are the mass of a house and ones that could have 1 billion times the mass of the sun. Like wherever you got enough of a dense region, you got a black hole. And one of the ideas to explain dark matter that I really like, but who knows, there's no observational evidence that this is true, is that it's explained by these primordial black holes. That you could explain all of dark matter by either having black holes that had about the mass of an asteroid, of a heavy asteroid, or black holes that have about 1,000 times the mass of the sun. And different numbers of both of those would perfectly explain dark matter. They would behave in all of the ways that you would expect dark matter to behave. But there's no observational evidence that these primordial black holes exist. So we have to just wait for someone to find something. If you want to support the work that we do, why don't you consider joining our Patreon club? Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Do you want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed and get the overtime segments as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Thanks to everyone who has already subscribed, and welcome to the recent newcomers: Joe Mansfield, Sylvain Gaudreau, Dr. Linda Newman, Kristen Rosier, DPD, Clarence Chumney, Chris Foley, Richard Williams, David Dillon, and Tony Zelina III. Join the club at patreon.com/universetoday. John Docherty: how good is the aurora out your way, and could you recommend a decent app that alerts in real time? So where I live on Vancouver Island, I am at about the 50th parallel. And for Canada, that's tucked in right along the border with the United States. But there's a lot more Canada to the north of me. But we do see auroras here. I would say we get an aurora every month or so where I am, to some degree. And maybe a couple of times a year, we get the ones that are just amazing and incredible, and people take wonderful pictures of it. And I wish that I hadn't slept through it. And there's been a few occasions where we've kept our eye on the aurora alert status. And when the activity is rising, we go and set up at a beach to the north and we watch the sky, and every now and then it's stunning and it's totally worth it. And you're like, I'm always going to do this from here on out. So, and then you forget, and then you sleep through it and everyone tells you they saw the auroras and you kick yourself and the cycle continues. But I think most people don't realize how accessible auroras are. Like where I am at the 50th-ish parallel, you can see them for sure, but you can see them down sort of midway from here to the equator. So I would say the mid part of the United States, the middle of Europe, like maybe Spain and above, Japan, places in Asia, northern Asia, you can definitely see auroras. The same goes for people in the southern hemisphere, people in Argentina, people in New Zealand, Australia. The closer you live to the equator, the harder it is to see an aurora. You need more insane aurora activity before you're going to get any kind of view in the sky. And so getting an app is the best way. The app will tell you when the aurora activity is high, that you've got a really good chance of seeing it. It'll tell you when's the best time, and you sort of check to see if it's going to be night for where you are. And then it's a leap of faith, right? Because then it is like, we probably won't see an aurora, but if we do see an aurora, it will be an experience of our lifetime. And the aurora, like the big auroras that I've seen, are some of the most memorable events. And I'll share a video of the aurora that we saw, and you'll see it looked even better than this. It was incredible. Like just these sheets of green that cover the entire sky from horizon to horizon, shimmering and floating. But if you live farther south or closer to the equator, then you just have to time it better, know a place to go, take a risk. The other thing you can do is take a vacation. Go to the Yukon in Canada, go to Iceland, and the chances are you'll see an aurora while you're there because it's so far north and has a lot of activity. Now, I don't have an app to recommend, partly just because, partly because I haven't found a good one. I haven't found like the best aurora app. I've tried a few and they're kind of cluttered with ads and they aren't that effective and not very stable. So if you have a recommendation, go ahead and put them in the comments, and so we can sort of triangulate on what is the best one. And I would love to add an aurora app to my phone. Bob, do gravitational waves travel at the speed of light? Yes, gravity travels at the speed of light. And this was one of the questions that scientists always had, was is the speed of gravity the same as the speed of light? That if you made the sun disappear, would the light coming from the sun match? Like, would we, when the Earth noticed that the sun was no longer there and just started to drift in a straight line through the Milky Way, would it also get cold because there'd be no sunlight instantaneous? They'd always assumed, and all the calculations that had been done, it kind of matched that yes, the speed of light and the speed of gravity are the same, but it was the kilonova event that finally gave us this precise measurement. So when you had these two neutron stars that collided with each other and sent out this incredible flash of light, and also the gravitational waves that were detected by LIGO and Virgo, you got this perfect match. And what's even more amazing was that you got the gravitational waves a little bit before you saw the visible light in the sky. And so you weren't detecting the gravitational waves from the collision, you were detecting the gravitational waves from the enormous amount of mass from the two neutron stars that were spiraling inward and putting off these gravitational waves as they were getting closer and closer and closer until they collided. And then when they collided, there was no longer the gravitational waves, then there was the radiation that was coming from the explosion. And both of these crossed hundreds of millions of light years of distance to reach our detectors, and they arrived in the right order. You got the gravitational waves, and then you got the flash within a few seconds of each other, exactly as you would predict if the speed of gravity is the same as the speed of light. Rebecca Smith, how do scientists know how many black holes are in the universe? For the longest time, astronomers had no idea how many black holes there were in the universe. Like, we knew of one black hole. We knew of Cygnus X1, which is, a few thousand light years away from us because of the radiation coming from the star and the black holes. They were interacting with each other. And then within the last couple of decades, astronomers started to realize that there were these supermassive black holes at the hearts of galaxies. And so astronomers would use that to say, well, if there's one at the heart of every one of these galaxies, count up the number of galaxies, and that's how many black holes there are. But like, how many black holes are there of the stellar mass variety inside a galaxy? And astronomers really had no way to work out that number. But thanks to LIGO and the ability to detect gravitational waves and the number of detections that they're making, like, you don't hear this anymore because they're happening so often, but there are gravitational wave alerts going out into the astronomical community almost every day now. And this is because we're in the fourth run of LIGO, where they've upgraded the technology each time. And they went from no detections to a couple of detections to a detection every week. And now we get multiple detections every week. You can actually go to this place called the GRACE website, and they give you real-time gravitational wave detections that are just sent out, just like the raw detection without any real scientific work done. And then scientists can look at the detections and try and figure out if it is a real gravitational wave collision. So you've got enough of these gravitational waves, different sizes, masses of black holes interacting with each other in different parts of space, that astronomers are starting to get this statistical number of black holes that are out there across the universe. And there's a great article that came out from Starts with a Bang, Ethan Siegel, who I've interviewed here on the channel. And he wrote a post talking about this, that astronomers have come up with a rough estimate of the mass function of black holes. And the mass function is where you kind of say, like, imagine the bell curve of all the different masses of black holes that are out there. There are this many supermassive black holes and that many 10 mass black holes, solar mass black holes, and sort of where they all fall along that. And their estimate is that there are 40 quintillion black holes in the observable universe. So if you add up all the black holes in all of the galaxies, you get 40 quintillion black holes. So astronomers think there are 10 million black holes in the Milky Way. That's an estimation that was developed based on Gaia data, looking at the numbers of various compact objects in the Milky Way, but we're not sure if the Milky Way is a good comparison. So there you go. There's your number, 40 quintillion. And they found that out through the increasing number of gravitational wave detections that have happened. I love that, right? That this is new, that thanks to gravitational waves, which is just wizardry, like it's sorcery already, you can detect black holes colliding every couple of days across the universe and use that to make these estimates of the amount of black holes there are in space. Thomas Quick, I've always wondered what would happen if you were too close to a large gravitational wave event. If you were too close, you would be torn into pieces. Like a gravitational, when you think about a gravitational wave moving through space, and you sort of, and you see the pictures where, the planet gets distorted, sort of pulled and squished, and yet doesn't get torn apart. That's only because the gravitational waves are very long and very gentle, and the amount that is being pulled apart is tiny, but it's real. And you know that it's real because we couldn't detect it if it wasn't real. Like what's actually happening is you've got these lasers that are firing these laser pulses down these long arms in the detector, and they're bouncing back and forth, and they're calculating, and they're actually interfering the light as it comes back in, and they're using that to calibrate along those two lines. And then if one of the arms gets stretched, then the light is no longer interfering nicely. You get this detection. And the only way that happened is for it to physically be pulled apart a bit and then put back together as the gravitational wave pulls past the Earth. And, here we are hundreds of millions of light years away from the event, and yet it can still pull the Earth apart enough that it's detectable by our scientific instruments. But if you got closer, then that force would not be gentle. It would be tearing you apart. But the problem is that if you're close enough to, say, two black holes that are in the process of colliding, their gravity, the tidal forces that are coming from those black holes, the radiation that's coming from the accretion disks around them would be lethal in so many ways. Like the gravitational waves would be the icing on the cake from all of the other ways that you experienced harm by being close to merging black holes. But it's real. Like it really would be there, and it would cause you damage if you got too close and you were somehow resistant to tidal forces and radiation. Millie Wilcox. Top 3 must do before you die astronomical experiences you would recommend to others. Yeah, I've got 3. Absolutely. So number 1, we talked about this earlier, auroras. See an aurora. Get an aurora into your eyeballs. 2 is a total solar eclipse. Now, we had the one back in 2017. We've got another one coming up in 2024. I'm going to go and definitely watch that one. If I were you, make your travel plans, go and see a total solar eclipse. There are people who they see one of these things and then they become eclipse chasers. They go around the world watching the eclipse. And if you've ever seen a partial solar eclipse, it is like an eclipse that is 99% partial is not a total solar eclipse. It is not good enough. It is underwhelming. If you told me that a 99% solar eclipse was going to be happening and I would have to drive to go see it, or I could stay where I am and see an 80% total, I will stick around and just watch the partial eclipse from where I live. They're not worth traveling to. But if you get to a total solar eclipse, it is night and day. That when the moon finally passes in front of the sun and blocks it, then the corona, which is the outer atmosphere of the sun, becomes this ghostly halo around the moon that normally you just can't see, and yet it's always there. And we didn't know about it until we saw these eclipses. You get this sunset, but like normally when you're outside and it's sunset and you get still kind of light in the direction that the sun went down, and then it's darker on the opposite horizon. Well, when there's a total solar eclipse, everything goes dark, like the whole horizon. It's the weirdest experience. And the birds and the animals go quiet for a second while this is happening. It gives me chills to think about seeing another total solar eclipse. So, and they're not like, unless you're really lucky and you live in a place that's got the path of a solar eclipse, but I would make a trip. Like if you want an experience in your life, go see a solar eclipse. And then the third one is to watch a rocket launch. And that one is a surprisingly easy one to knock off of your bucket list, which is that there are an enormous amount of rockets taking off from Cape Canaveral right now. Every couple of days, another batch of Starlinks head off. And so it's easier than ever to watch a rocket take off. And the view that you get from a place like, say, Cocoa Beach, which is just south of Cape Canaveral, is pretty good. And so you can go down to the beach, sit there and watch the rocket take off, and you can feel the shock waves of the rocket going past you, and you can see the rocket head off into space. You can get closer, but like not a lot closer. You can go actually onto Cape Canaveral NASA sets up events at the Kennedy Space Center, and you can watch them from there, and it's fun. But just being anywhere there is great. And like, I love that you could just sit on the beach, you know, with a cold beverage in hand, sitting on a lawn chair, and just watch rockets take off from that location. And it's, you know, it's a big airport, Orlando. You fly into Orlando, and then you drive out to the Space Coast, book a hotel, reasonably inexpensive trip, and you are watching rockets fly into space. And everybody who lives in Florida is like, boring, but for the rest of us, it's totally worth doing. So go see an aurora, see a total solar eclipse, and watch a rocket launch. All three are totally doable. Angel, when do you think the data is going to come out on TRAPPIST-1 planets D, E, and F? And do you think any of these planets will have an Earth-like atmosphere? Thank you. TRAPPIST-1 is the most intriguing planetary system out there. There are 7 Earth-sized worlds orbiting a red dwarf star, and now James Webb has directed at TRAPPIST-1b, which is the closest in planet, TRAPPIST-1c, which is the second closest, and both of these appear to be airless. They are like super Mercuries. And so next comes D, E, and F, and these are the 3 worlds that are located within the habitable zone of TRAPPIST-1. And the question is, has James Webb looked at it? And the answer is yes. Do we know what the answer is? And the answer is no. The astronomers are crunching the data right now, and they haven't released it yet. Do I think it's going to have an atmosphere? I have no idea. Like, you know, there are plenty of really skilled exoplanetary scientists who are studying these planets, and they have an opinion, and they believe that it's intriguing. But based on the interviews that I've done, red dwarf stars are terrible. They put out these enormous, powerful solar flares. And it was like, one of the hopes was that they would spot something like Venus's atmosphere on the TRAPPIST-1c. They thought, okay, well, it's far enough away from the planet that maybe we're going to get a runaway greenhouse effect, something like Venus. And they didn't get that. Airless. And so it could very well be that the enormous megaflares that are coming off of the star are just thrashing away any atmosphere that could hope to form on the planet. These flares are devastating, and the planets are a lot closer to the star than what they would be here in the solar system. So if it turns out that there is no atmosphere on any of these worlds, I will not be surprised, because that will tell us how bad those stars are. And that's like one really interesting data point. And then as astronomers find other examples of terrestrial planets inside the habitable zone of red dwarf stars, and they image the atmospheres of them, and they don't find any atmosphere, it's going to start to build the case that you're not going to find atmospheres at planets around red dwarfs, and that these are not places to look for life, which would suck because they're easier to observe than Earth-sized worlds orbiting around sun-like stars in the habitable zone, which we haven't even found yet. Jonathan 98. So when thinking about the Fermi paradox, I always wonder how close we'd have to be to a copy of our civilization to be sure that we would be able to detect it with current technology. So right now, we probably don't have the technology to detect another version of the Earth that was farther than about 100 light years away from us. But if it was within 100 light years, and there are like about 50,000 stars within 100 light years of us. So there's a lot of stars, and there are a lot of planets that have been discovered around those stars. We could detect the presence of life, of a modern advanced civilization on one of those worlds. And there's like dozens of ways that we could search for evidence of a technological civilization. We could watch the X-rays coming from their antimatter drives. We could watch for them creating a Dyson sphere around the star. Like, there's a lot of like real science fiction ways that we could do it. But there's like 2 practical methods that we could use to search for a civilization that wasn't trying to send us a message. Like, if they're sending us a great big tight beam radio signal, we could absolutely detect it. But if they were unintentionally announcing their presence, there's some ways we could do it. One is that James Webb has the capability to detect the presence of chlorofluorocarbons on a type of planet like Earth within about 100 light years of us, like maybe a little farther than that. And of course, chlorofluorocarbons, those are the refrigerants that were used for decades that were causing damage to the ozone layer, and so they stopped doing it. But there is still the presence of those chlorofluorocarbons in our atmosphere. And so if we took Earth and moved it 100 light years away from us, and then we pointed James Webb at Earth, it could detect the presence of the chlorofluorocarbons. And you don't get chlorofluorocarbons from volcanoes right? You only get that from an advanced civilization making those chemicals in some kind of industrial process. The other way is by the leaked radio emissions. Right now, we don't have the ability to detect the leaked radio emissions of another planet. You always talk about how, Earth's television signals are floating off into space, but they are fairly weak signals and they are expanding out in all directions. And so it's going to be very difficult for any other civilization to detect the presence, to watch our 1950s TV shows. But the radio transmission that comes from air traffic control systems is quite intense. It's a very sort of bright spot on the planet. And right now we're building a radio telescope called the Square Kilometer Array. And it is going to be overall 1 square kilometer of radio telescope that will be like the James Webb Space Telescope, but of radio telescopes, a super telescope. And we're still about 8 years away from this thing coming online. But when it does, one of its capabilities will be to detect the presence of Earth's radio chatter from about a distance of 100 light years away. And so if there was another Earth within 100 light years, James Webb could detect the chlorofluorocarbons, and the Square Kilometer Array could detect the radio emissions coming from, say, its air traffic control system. So that's pretty cool. All right, those are all the questions that we had today. Thank you, everyone, for asking your questions in the YouTube comments, as well as all the people who showed up. Remember, we do the show live every Monday at 5 p.m. Pacific time. So subscribe to the channel. You'll get a notification when we go live, and then you can show up and join the live show. Yeah, I'm going to talk about something a little different in a second, a message to other people who create content on the internet. But first, I'd like to thank our patrons. Thanks to David Richards, Mark Anstis, Joel Yancey, Antonio Lofilara, Dustin Cable, Vlad Chiplin, Modzo, George, David Giltonad, Andrew Gross, Jeremy Mattern, Josh Schultz, Jordan Young, and the rest of our patrons. All your support means the universe to us. If you've spent any time making any content on the internet, you have experienced the haters. And like people who just write crap on you. And as a person who has to get up every day and you're like, I made this, and then people just give you a hard time about what you do, it is very hard on your soul. Which is fine. It's part of the job. I mean, I know kids want to be YouTubers. So, but if you're a creator, one thing that I highly recommend to you is that you get a chance to talk to the people who enjoy your creations. So one of the things that I do, and I don't publicize this much, but I guess I'm doing this right now, is that when you sign up as a patron, I send you an email that asks you if you want to do an interview with me. And then and it's really me, we actually sit and have a Zoom meeting. We talk for 15 minutes and I have a bunch of questions for you, but it is one of the best parts of my day because I get a chance to talk to the people who consume the content and aren't the haters, the people who quietly appreciate the work that we do and have constructive feedback, but also just aren't giving you a hard time just in general. And every time I finish one of these interviews, I'm so excited and so enthusiastic to keep doing this work. And so if you're a person who is working on any kind of creative project and you just feel like you're going uphill all the time, figure out a way to have a conversation with the people who consume your work. I don't know how. Offer to interview them like what I do, and you will it'll be the high point of your day and make you feel great and sort of give you that sort of much more balanced perspective about what it is that you do and why what you're creating has value in this world. So that's it. Talk to your fans. It'll be some of the best experiences that you've ever had, I promise. All right. Thanks, everybody, and we'll see you next week.